Okay. So, having proved the previous theorem, so we will investigate slightly into the convergence at a point of continuity. Okay. So, a Fourier series of some function f converges to f at a point x if f of x is written in the form a naught plus limit n going to infinity summation k equals 1 to capital N a k cos k x plus b k sin k x. So, there are various notions of convergence, whether it is pointwise convergence or uniform convergence, etc., right. So, I would basically refer you to analysis lectures for these various notions. Now, what is this saying? That I can take a series infinite series expansion, and that series expansion is very close to the true function, that is it converges to this function as n goes to infinity, right, capital N goes to infinity. So, with this we can state a theorem. Suppose f is continuous and a 2 pi periodic function. It is continuous and it is 2 pi periodic. Then at each point x where f dash of x, that is derivative of x, is defined, the Fourier series of f at x. So, at every point x you have an expansion, right, at x converges to f of x. So, suppose f is continuous and 2 pi periodic, then at each point x where the derivative of the function is defined, the Fourier series of f at x converges to the true function f of x. So, we will prove this result. There are many steps in the proof of this result, and it is a long theorem, but I hope you will appreciate the details in this result. Now, for a positive integer capital N, let us define the sum Sn of x is a naught plus summation k equals 1 to capital N a k cos k x plus b k sin k x. We saw this summation. Now, what we need to show is very important, right. We have to precisely put it in mathematical terms. Sn of x heads to f of x as n goes to infinity, right. This is what we need to show. Now, for this let us rewrite Sn in a slightly different way. Okay. So, we will see this through a sequence of steps. So, step 1. So, we substitute the Fourier coefficients and when we do that we can write Sn of x a naught is 1 upon 2 pi integral minus pi to pi f of t dt, and then a n is 1 upon pi integral minus pi to pi f of t cos k t dt. So, basically I write as summation k equals 1 to capital N, this is a series sum f t cos k t times cos k x. You see, deliberately I have gotten this t and x because it is a definite integral, right. So, I can always write it in this form. So, this 1 upon pi could be here, I have just pulled it outside, but you can see this is basically your a n, right, and then your b n is, I can put this here itself, this is basically integral minus pi to pi f of t sin k t sin k x, and I have to put a dt here whenever I write this in integral, I have a dt. So, now we can pull, so we can pull all the terms together, right, and I can say I have a cos k t cos k x, then there is a sin k t sin k x, right. I can pull all the terms together. So, I can say Sn of x. So, and I can use this formula cos a minus b is cos a cos b, this is the compound angle formula, cos a cos b plus sin a sin b. Using this, I call this equation 1. We can simplify Sn of x. This is 1 upon pi integral minus pi to pi f of t, there is a half factor outside. So, 1 by 2 pi integral minus pi to pi f t dt is this term. So, I will put a dt here. Okay. So, 1 upon pi f of t is a half factor, that dt is this term. Okay. Now, I have f of t outside, I can pull this out, right. I have a cos k t cos k x sin k t sin k x, and I can write this as summation k equals 1 to capital N cos k into t minus x. Right. The same Fourier series is written like this, slightly different way. Okay. This is sort of straightforward. Now, in step 2, we have the following lemma. My writing is a little more unconventional. I could start with sequences of definitions, lemmas and theorems, and I say just invoke that lemma here, but I do not want to do this way because I want you to get a feel of how you want to progress in proving the main theorem, and a step could be potentially a lemma or it could be just some portion of a derivation. Now, for any number u belonging to minus pi to plus pi, 1/2 plus cos u plus cos 2u plus so on cos n times u. This is basically sin n plus half u over 2 sin u upon 2 for u not equal to 0 and equals n plus half when u equals 0. When u equals 0, you can just apply L'Hopital rule and you can obviously see that this is sort of valid to this equation. Let us or if you just put u equals 0 directly, you have n terms here, n plus half. Both the ways you can immediately check the veracity of this result for this condition. Let us look at this part. This is also very easy to straightforward, just a trigonometric sum. So whenever you see these series sums, you have to get the Euler formula in your mind. Okay. So e power ju power n is cos n u plus j sin n u. Now consider 1/2 plus summation k equals 1 to capital N cos k u. Now when k equals if I want to replace k equals 1 to n by k equals 0 to n, then what I do is I put a minus half factor out plus real part of the summation k equals 0 to capital N e power j u power k. This is not really difficult to see, right? K equals 0, this is 1. So 1 minus half is half, you have half here, and the rest is basically take the real part, you are going to get the cos. No big deal, right? This is minus half plus real part. Now this is a geometric sum, so you can write this in this form, power j times n plus 1 u divided by 1 minus e power j u. Right, the common ratio is e power j u and the first term is 1. So a into 1 minus r power n over a into 1 minus r power n over 1 upon 1 minus r power n plus 1 over 1 minus r. Okay, you apply the geometric series sum here, is what this is what you are going to get. Now you simplify this further, it is minus half plus real part, I will get e power minus j u upon 2 minus e power j n plus half u right. If I just multiply and divide by e power minus j u upon 2 for both numerator and denominator, I get it in this form. Okay. So what do I get here? So I get a minus half plus a real part now e power minus j theta is cos u upon 2 minus j sin u upon 2, that minus and minus will cancel, it is going to be a plus, right, cos theta. Okay, this is a minus here, minus j sin u upon 2 minus this is cos n plus half u minus j sin n plus half u. Okay. Now, this is again cos u upon 2 minus j sin u upon 2 minus, so there is a big minus here and then I just have to put a brace here appropriately, and there is a plus here. Okay. Now, here it is cos u upon 2 plus j sin u upon 2. It is just routine algebra, right. If you are very shrewd, you will notice that just group the j terms appropriately here, right, and then just it will cancel out. So, this cos u by 2 minus cos u upon 2 will cancel out. So, the denominator you will be landing up with minus 2j sin u upon 2, right. So, you have, if you simplify this carefully, it is minus 1/2 plus 2 sin u upon 2, and in the numerator it is sin n plus half u plus sin u upon 2. I mean, how do I get this? There is a minus j, there is a minus j, this is minus 2j sin u upon 2, right, because this cos u by 2 and minus cos u by 2 will cancel out, and then you will here have cos u upon 2 minus something, and then you group the j terms, you will have a minus j times sin u upon 2 plus sin n plus half u, right, and the j and j will cancel, the negative will cancel out, and then you will end up with, taking the real part, you will end up with this equation here. It is sort of straightforward, and this you could simplify, right, because this sin u upon 2 and this will cancel out, this half and half will cancel out. So, therefore, you will end up with sin n plus half u divided by 2 sin u upon 2, and this is when u is not equal to 0. When u equal to 0, you apply L'Hopital rule and you will land up with n plus half, because denominator will cancel out. Okay, so, this is indeterminate form, this is 0 by 0 form, apply L'Hopital rule, differentiate the numerator and the denominator and take the limits as u goes to 0, and you will land up with n plus half, and this is consistent because you just add the terms. When u equals 0, you have n terms, n plus half is what you have. Now, this proves this lemma, but we have just addressed the second part, second step of the proof of this theorem. Now, we go to step 3. Let us evaluate the partial sum of the Fourier series. We will evaluate the partial sum of the Fourier series. So, now we have Sn of x is 1 upon pi integral minus pi to plus pi f of t, and we have 1/2 plus summa k equals 1 to capital N cos k times t minus x dt. Now, I write this in this form 1 upon 2 pi integral minus pi to plus pi f of t. Using the previous lemma, right, I can simplify this quantity as sine n plus half t minus x divided by sine t minus x upon 2 dt. The 2 factor that appeared, I just pulled it here. Okay, just observe this 2 here. Okay, is a factor of 1 upon 2 here, right? That 2 I am pulling it at this step. Now, if we define Pn of u as 1 upon 2 pi sine n plus half u divided by sine u upon 2. If I define this function Pn of u as this form, then I can write Sn of x as integral minus pi to plus pi f of t Pn t minus x dt. Right, this is our sort of simplified form, right, but let us go one step further. Let u equals t minus x, just a change of variable. So, therefore, du is dt. I can write Sn of x is integral minus pi to pi f of u plus x Pn of u du. So that it is in this form, this is like the kernel. Okay. Say, wonder why? The limits on the definite integral remained unchanged though it had to be pi minus x and minus pi minus x when you had to do a change of a variable here. Now, let us go to step 4. There is an interesting property, call this as a lemma. Minus pi to pi is a trivial result. Pn of u du equals 1. That is, if you integrate this kernel, it gives 1. Now, how would you prove this result? So, basically you write Pn of u in the original form 1 upon pi 1/2 plus cos u plus cos 2u plus so on till cos n times u. Now, when you integrate all these functions cos u, cos 2u, so on till cos n u, that just vanishes over the cycle, and 1 upon 2 pi you integrate from minus pi to pi, it is 1, right. This is basically straightforward, there is no big deal here. Now, we will go one last step, which is step 5. So, we start where we were in step 3. So, from the previous lemma, right, from step 4 lemma, I can write f of x is integral minus pi to plus pi f of x p n u du. Trivial, right? I just folded f of x inside, because integral minus pi to pi p n of u du is 1. So, it is a very trivial result. So, just observe that I am integrating with respect to u, not x, right. I am integrating with respect to u and not x. Now, this trick is important. We are home if we show integral minus pi to plus pi f of u plus x minus f of x times p n of u du heads to 0 and then goes to infinity. This is the important part. The second part is no big deal, because this was I am integrating with respect to u and f of x is a constant. So, therefore, that is no big deal. This is important, because when I take f of u plus x and then I fold it, because now there is an argument u which is appearing in the expansion of the function, and I have to show that this heads to 0 as n goes to infinity. Now, you will appreciate why this kernel and all these things are playing a role, right. So, now let us simplify this. Now, 1 upon 2 pi is what we have, integral minus pi to pi f of u plus x minus f of x divided by, there is a negative sign here, divided by sine. So, what I do is I just replace it by the kernel, sine n plus half times u du. Now, invoking previous theorem, limit k going to infinity integral minus pi to plus pi f of x sin k x heads to 0 as k goes to, that is as k goes to infinity, right, except at u equals 0, pi, minus pi. Right, this is some function. I am basically expanding this, and when this is basically modulating, as n goes large, this basically vanishes. So, now let us see what is happening here. So, let me write this function g of u as f of u plus x minus f of x over sin u upon 2. So, this function is continuous except at u equal to 0 over minus pi and pi, except at u equals 0, right. When u equals 0, it is in the form 0 by 0 form, therefore, it is continuous except at this point. Now, the derivative of this function can be written as limit u going to 0 f of u plus x minus f of x over u, right. It is the f of x plus u minus f of x over u as u going to infinity, that is the derivative of the function. That is the reason we say f dash exists by hypothesis, where the derivative exists. This is where I mentioned, because we will make use of this fact. Now, consider limit u going to 0 f of u plus x minus f of x divided by u times u upon 2 divided by sin u upon 2 times 2. So, this is by definition, this is f dash of x times this is 1, this is 2, this is 2 times f dash of x. Now, let us define g of 0, because g of u is what is that function, right. G of u is that function which we defined like this, and we want to look at that limit as u goes to 0, because that is the point which we are interested in, because it was discontinuous point. So, if we define g of 0 as 2 times f dash of x at those points x, g of u extends across u equals 0 as a continuous function, right. At that point it is discontinuous, but if I put this in this form, it extends as a continuous function, right. So, therefore, we can conclude that this is at all the points, that is u equals 0 and the rest of the points, integral minus pi to plus pi f of u plus x minus f of x times p n u du, this heads to 0 as n goes to infinity, and we close this theorem here. Okay, so, there were two subtle points we had to note. One is u being equal to 0, and when u is not equal to 0, and when u not equal to 0, then we have no problem, because we invoke the previous theorem, and therefore, that integral basically vanishes, right, because you have some term here which is of this form times some frequency, large frequency here, and that basically dives to 0, and we invoke the previous theorem, right. So, therefore, this is true, but when u is equal to 0 we have a trouble because we have a 0 by 0 form. So, we have to consider it carefully, and using the derivative definition for the function f of x, we show that if this is possible and we extend g of u as a continuous function with u of 0 point, then still we are okay, and therefore, this this expansion, the Fourier series expansion in the limit form, it converges to the function itself. Okay. So, in the next lecture we will discuss the convergence at a point of discontinuity, and then we will subsequently build our notions of various other forms of convergence of the Fourier series. We will stop here.